Michio Kaku once remarked that we will need to revise our textbooks on the origins of the universe. For years, scientists have eagerly anticipated a particular image, which has now been released. This image from the James Webb Space Telescope reveals uncommon cosmic processes that challenge our current scientific understanding. Since the launch of the telescope, not only have our theories about the universe's beginnings been tested, but even exoplanets have started to defy our understanding of physics, completely upending our ideas. What new insights and answers will scientists discover from these findings? We are now witnessing a complete upheaval of traditional scientific rules. The James Webb Space Telescope is transforming our view of the universe, and each new image from this marvel of space exploration is groundbreaking. James Webb, the telescope's namesake, would have been proud. Although Webb was not a scientist, but rather came from a business background, he understood the importance of space exploration for humanity. As NASA's head in the 1960s, Webb revolutionized space travel, launching the Apollo program and advocating for space missions. Today, scientists are astonished by the telescope's capabilities, as the images it produces are so sharp and clear they take our breath away. For the first time, we have detailed studies of exoplanets located light years away. The telescope is revealing to the scientific community that they have been relying on outdated discoveries and theories for far too long. Initially, many researchers were filled with uncertainty and discomfort, as everything they once believed could now be disproved. Michio Kaku, a prominent astrophysicist, remains optimistic about these new developments. He has long argued that previous theories were inadequate, pointing out that our inability to integrate the universe of subatomic particles with that of structured matter shows we don't yet fully grasp the fundamental processes of the universe. Now, exoplanets are also challenging the laws of physics. It's astonishing. At first, it was only ancient worlds that didn't fit into our cosmological models, followed by black holes and massive structures older than 13 billion years, when the universe was still in its infancy. Now, even planets are testing our old understandings. The latest images from the James Webb Space Telescope feature exoplanets that defy our previous conceptions of planetary data. The telescope's sharp eye and sophisticated array of spectrometers have allowed scientists to perform detailed analyses of these planets. It can break down even the faintest light signals into their individual components, analyzing traces of elements, gases, signs of water, and other features that reveal the size and orbits of distant planets. As Webb uncovers more anomalies and extremes, scientists are facing some truly perplexing discoveries. One striking example is K2-9b, an ultra-hot Neptune that orbits so close to its star that its surface temperatures are high enough to break apart water molecules into hydrogen atoms. Its extreme proximity to its star leads to a phenomenon called atmospheric blow-off, where the planet's atmosphere is literally blown away by the star's intense heat. This discovery is unique among all known planetary environments and presents a serious challenge to our current understanding. Other discoveries are equally mind-boggling. For example, WASP-76b, a giant exoplanet, experiences iron rain on its night side. This planet orbits its star in a perfectly locked orbit, resulting in extremely hot and cold sides. On the hot side, metals are vaporized and carried to the night side, where they condense into iron rain. Researchers are confronting extreme conditions that provide surprising insights into the planetary processes at work, raising more questions than answers. Even more intriguing is the discovery of planets that orbit their stars in the opposite direction of other planets in the same system. Such findings force cosmologists to reconsider theories about the dynamics of planetary systems and the forces that influence their orbits. WASP-17b is an example of such a world, an enormous gas giant similar to Jupiter that orbits its star in a retrograde direction, contrary to the star's rotation. This was previously thought to be impossible according to current planetary formation theories, which suggest that all planets in a system should orbit in the same direction as they formed from the protoplanetary disk. One hypothesis suggests that gravitational interactions with passing stars or massive planets can dramatically alter a planet's orbit after its formation. Another possibility is that a gravitational interaction between several large planets could push one or more into a retrograde orbit. Interestingly, We don't have to look far from our own solar system to find unusual planets. In the Kuiper Belt, for example, astronomers have discovered the dwarf planet 2018 VG18, which has been shown to be unusually dark and red. Spectrometers from the James Webb Telescope suggest that this planet is likely rich in complex organic compounds, known as tholins. Despite its significant size and peculiarities, 2018 VG18 remains unnamed because its exact orbit has not been determined. Its composition, rich in organic substances that could potentially be the building blocks of life, and its surprising color, don't match those of other dwarf planets in the Kuiper Belt. This raises important questions. Where did this planet come from? How did it form? And why is it so difficult to observe? Another fascinating discovery involves rogue planets, planets without a star. Normally, planets form in the dust and gas left over from star formation, remaining gravitationally bound to their star. However, rogue planets defy this expectation, drifting freely through space without any star. How do they survive in the cold, hostile environment of space? Rogue planets can form in a number of ways. One common scenario is that they are ejected from their original star system due to dynamic interactions with other planets or close encounters with other celestial bodies. Another possibility is that they formed independently in regions where gravity was strong enough to create planets without the need for a star. These discoveries are reshaping our understanding of the universe, and as we continue to explore with tools like the James Webb Space Telescope, we may find even more phenomena that challenge everything we thought we knew about the cosmos. In a star-forming region where objects lack enough mass to initiate nuclear fusion, a new class of celestial bodies, known as jumbos, has been discovered. These are Jupiter mass-like objects that did not accumulate enough mass to become stars. Jupiter, the largest planet in our solar system, almost reached the mass required to trigger nuclear fusion processes. The James Webb Space Telescope, JWST, recently made a stunning discovery by identifying 80 such free-floating Jupiter mass objects in the Orion cloud. What is particularly intriguing is that 40 of these objects are in pairs, orbiting each other in close proximity within the Orion cloud. This discovery is both unusual and scientifically surprising. The sheer number of these objects is likely due to the Orion cloud being one of the most active star-forming regions in the galaxy. However, further analysis revealed that these objects are not true planets but rather fall into a category between planets and brown dwarfs. Brown dwarfs are failed stars, objects that are too small to initiate fusion but are still considered stars due to their formation processes. This raises a new question. What processes in the Orion cloud lead to the formation of these failed stars that behave like planets, freely moving through space in pairs? These objects challenge our understanding of stellar and planetary formation. The discovery suggests that such free-floating objects might be far more common in the universe than previously thought, although their rarity in our knowledge may stem from the fact that we have only recently been able to identify them. Identifying and studying these objects in the depths of space has been challenging, but the JWST has enabled a breakthrough in this area. The scientific community is excited, but also overwhelmed by the new anomalies and discoveries. As some scientists suggest, the revelations brought by JWST may signify the end of established science. As physicist Michio Kaku remarked, we may need to rewrite our textbooks, yet answers to these new questions remain elusive, with researchers frantically searching for explanations. The JWST, named after James E. Webb, a former NASA administrator who played a key role in advancing space exploration during the Apollo era, represents a monumental leap forward in our ability to observe the universe. Launched in December 2021, the telescope is located at the second Lagrange point, L2, about 1.5 million kilometers from Earth. This position offers several advantages for cosmic observations, including a stable thermal environment and an unobstructed view of deep space. Unlike its predecessor, the Hubble Space Telescope, which mainly observes invisible and ultraviolet wavelengths, the JWST is optimized for infrared observations. This capability allows it to peer through thick dust clouds, study the formation of stars and galaxies, and even analyze the atmospheres of distant exoplanets. One of JWST's primary scientific goals is to explore the origins of the universe by studying the light from the most distant galaxies. This will provide insights into the early stages of cosmic development, just after the Big Bang, including how the first stars and galaxies formed and how they influenced the evolution of the universe over billions of years. JWST also aims to revolutionize the study of exoplanets, planets that orbit stars outside our solar system. The telescope's advanced instruments can study the atmospheres of these planets in incredible detail, identifying chemical signatures that reveal key properties such as temperature, composition, and even the potential for habitability. Before JWST, astronomers relied on indirect methods to detect exoplanets, such as the transit method, which detects slight dips in a star's brightness as a planet passes in front of it, and the radial velocity method, which identifies subtle wobbles in a star's motion caused by the gravitational pull of orbiting planets. While these methods have been highly successful, they provide limited information about a planet's size, mass, and orbit. JWST promises to transform exoplanet research by directly imaging distant worlds and analyzing their atmospheres, opening new possibilities for identifying planets that may harbor life. Understanding the diversity of exoplanetary systems and their atmospheres is crucial for determining the prevalence of life elsewhere in the universe. JWST's advanced technology extends beyond exoplanets and early galaxies to include a wide range of astronomical phenomena. The telescope's suite of instruments, including cameras, spectrometers, and coronagraphs, allows it to capture different aspects of the universe. For example, the near-infrared camera NIRCam provides high-resolution imaging across a range of infrared wavelengths, while the near-infrared spectrograph NIRSpec analyzes the light from distant objects to reveal their chemical compositions and physical properties. One of JWST's most remarkable features is its ability to conduct coordinated observations with other ground-based and space-based telescopes. This collaborative approach, known as multi-frequency astronomy, enhances our understanding of complex astrophysical processes and cosmic events. By combining data from various wavelengths of light, scientists can build more comprehensive models of celestial objects, from star-forming regions and black hole environments to the dynamics of galaxy clusters and the cosmic web. However, operating JWST comes with significant challenges. Its delicate instruments must function at extremely cold temperatures, close to absolute zero, to minimize interference from their own heat radiation. Additionally, its large, sensitive sunshield, roughly the size of a tennis court, protects the telescope from solar radiation and maintains its thermal stability. These engineering feats require careful planning and execution, representing years of collaboration among NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Despite these challenges, JWST has already begun to deliver groundbreaking scientific results. In July 2022, the telescope captured its first images of the universe, revealing a distant star-forming region in stunning detail. These initial observations showcased JWST's capabilities and set the stage for years of significant discoveries. Looking ahead, JWST will continue to push the boundaries of cosmology and astronomy. Its unique vantage point and advanced technology are poised to provide new insights into the fundamental questions of our existence. How did the universe begin? What are the origins of galaxies, stars, and planetary systems? Are we alone in the universe? As JWST embarks on its mission of exploration, scientists around the world eagerly anticipate the discoveries that lie ahead. Each image, spectrum, and scientific observation has the potential to reshape our understanding of the universe and inspire future generations to pursue the quest for knowledge among the stars.